welcome. My name is Kim. Thank you, Helmut, for the presentation. We, together with Alvaro and Tecnalia, we're going to present the HiPerform activities and introduce a bit the project. As you said, I'm going to focus on the functional safety and the concept phase, but Alvaro is going to focus more on the other part of the model, providing some validation methods and so on. So it will be this completely full view picture on the different safety activities. For my side, first, I'm going to introduce HiPerform with you. I think it's a really huge project with a lot of partners participating on that. So just had a picture of which is the main motivation, objectives, and which is the use case that actually we're focused on. Then we will jump to this functional safety in the concept phase, and we are going to follow the guideline for the ISO 26262. And we are trying to describe the different safety activities that we develop in the project. And at the end, we're going to, as you said, Helmut, to go through this STPA method and to explain how we use this STPA method in the project. Yeah, HiPerform is this high-performance wide bandgap power electronics. And I think that this is the main motivation of all the projects. So this is a semiconductor, a property of a semiconductor. And here it's the main wish is to analyze this silicon carbide and gallium nitride semiconductors technology and see how we can apply these semiconductors into electronics and electrics. Of course, we use these components for electronics and electrics, more focused on the electrics, voltage components, and so on. And we apply those components. So the application of this project is in the context of automotive domain. So basically, it's focused on electric vehicles, and this project has an impact on the chain of the electricity on the electric vehicles, from the off-board charging, inboard charging, DC-DC components, inverters, e-motors, and so on. So at the end, what it offers this project is different 6 use cases, with distributed in 5 different work packages, and so on. As you see here, there is a website. Our objective, of course, is with introducing these materials is to reduce the cost, and, for example, increasing the switching frequencies here up to 500 kHz, as well reduce the space, and reducing the space as well, trying to reduce energy losses, and of course having an impact on the thermal management system. So the introduction of these materials has a lot of impact on the chain of that. So we start from these components, but there's have impact on the analysis of the electronic power flow, then going to the thermal management, flow distributions as well, which is the impact on electronics, as well on the different frequencies and the impact on the different main boards. So as it's a multiple level project. And we are on the part of the application. As I said, this is different use cases. Our use case in the focus on the use case 4, and is focused on this electric drive system. Before this slide, I forgot it, but yeah, this is as I said, a European project, and there is a lot of partners involved. And I want to have here provide you the view of how many partners we participate in this big project. As I said, our main interest is in this use case 4, where we have an electronic drive system, and it's the will to analyze such components, such materials on the inverter and the e-motors. But for do that, we introduce these complete powertrains. As a particularities, not going through the slide, but as particularities is two in-wheel motors, so are not physically connected one to each other. So this is one of the particularities. And then as well, we will introduce as well the controllability of that, and as well we have some specific particularities on that. But just to have a picture on at the end the vehicle, the demonstrator that is going to go this powertrain is in this JAC vehicle. Is an electric vehicle, so we it already had an electric powertrain and battery and so on, but we are willing to introduce this new powertrain, is why we put it in the back. So it is, the front is a classical e-motor with battery powertrain, but in the back we introduce this, and we mainly focus on the development of this powertrain here in the back. Of course, it's our main interest here is the functional safety, is to cover all the activities of this, let's say, product development of the vehicle, to introduce the safety activities and to have this support during all the development of the product to guarantee the functional safety. For that, we put effort in the concept phase and to introduce the functional safety on this part of the concept phase. Here, of course, it's not we are not developing a vehicle from zero, from start. We already have a vehicle and we have to adapt to the circumstances. So how we already had an architecture. This is the old electric architecture that was provided for Tecnalia, that was supporting as well, of course, during this item definition. And here, of course, we have to, it's important in this item definition to check which are the boundaries, which are the interfaces on this to our new powertrain. And this is all this part of you define, okay, how our powertrain is going to interact within the architecture of the vehicle and the components. The main item, as I said, is the vehicle control unit. This is the main ECU where it controls the vehicle dynamics, the inputs from the acceleration, deceleration, and so on. And it's calculating as well. It's introducing this. What I said is just not the in-wheel motors, it's as well the different functionalities that we could have in this new kind of powertrain setup. And one of those is this torque vectoring. And here as well will be really important as well in the other part of the validation phase to analyze the impact on this torque vectoring on this powertrain. And the scope of this project is this PCU, that is it's at the end the main ECU. We will translate that to torque and speed that will be in this powertrain control unit, and this powertrain control unit will be the one who sends the impulses and manage the electrics for the inverter and e-motor. Once we define the item, we go through the HARA, hazard analysis and risk assessment. This is a picture of the different activities. Of course, what it's our will here, it's okay, we have a powertrain that is going to affect on the vehicle level, and we want to analyze the different malfunctions that you could have in this vehicle and in this vehicle, take into consideration the powertrain. And with these malfunctions, we're going to impact on the different scenarios. And here you can imagine the scenarios, so urban, driving to urban area, to a high speed, I don't know, all kind of different scenarios that you could put in the vehicle and in driving in the traffic area. And then we'll analyze the hazardous events and we'll subtract this ASIL determination. As you know, this ASIL determination that at the end it's goes together with the safety goal, and that's the main result of this part of the hard. For this powertrain in concrete, so we don't have a large list of functionality. Of course, it's just this acceleration, as I said, from these two in-wheel motors. It is the acceleration and taking into consideration the brake system and the regenerative braking. And then the other functionalities that we have in the main ECU, like traction control, that it comes from the legacy of the vehicle, but this new torque vectoring and others that we have. So you have to stop and think for one moment that this powertrain has no physical connection between the two wheels, and therefore, for example, there is no differential, mechanical differential, and so on. So all these things have to be software controlled, and of course needs an extra level of attention on the safety level as this safety critical component that it is. No? So here we subtract a list of 61 malfunctions. Of course, that malfunctions could happen in a different set of scenarios where you could go through different locations, traffic situations, speed ranges, environmental conditions, and so on. And here we subtract as well a large list of scenarios. And then you have to combine the malfunctions with the scenarios to see which are the relevant ones, the one who wants to analyze under the risk assessment, and which are the safety relevant, and which are at the end the ones that are going to provide with the safety goals and the ASIL classification. This is kind of the result that we had in this project. At the end, we had a list of 9 different safety goals. And of course, the ASIL was the higher level ASIL for almost all the functionalities as this safety critical component it is. Of course, that would have really similarities to a traditional powertrain, but of course has this particularity for this in-wheel motor. And here it will be how we are going to distribute this safety goal. But before, of course, we had this item definition, first step, then the HARA, and then we are ending this concept phase with this functional safety concept. And this functional safety concept has some preliminary activities like this, for example, preliminary assumptions or the different operation modes. And for example, these preliminary assumptions would be so, like, for example, to put an example, would be the situation if a driver is pressing the throttle pedal and the brake pedal at the same time. So what is the reaction of the vehicle? And that's misuse of the driver. You should take the decision if you include that on the safety identity or not. In this case, we decide, okay, this is like a misfunction of the driver, and we are not going to accept those ones, even though we could take into consideration. That's not excluding. We are not excluding that, but we are not including on this part of the safety concept. And we put as assumption, but of course we set up that this should not be allowed, for example. And then we have this different safety, the operation modes that as well could help us to have strategies while we are analyzing the powertrain to be introduced in a safety level for this critical system. As I said, the safety goals could be distributed in these 3 different groups. The first group is what could be like in a generic way for a traditional powertrain, this acceleration, and what you could have. For example, you would like to accelerate and you cannot, or the other way around, you don't want to accelerate and the vehicle accelerate by itself, or in the other way around for the braking as well. Then we have a second class that is really interesting for us, that is this part of the in-wheel motor. So it's 2 independent motors, And you have to as well take into consideration that the in-wheel motor, it's installed inside the wheel. So if there's an issue, the possibilities to introduce safety measures are really not so high. So you have to be really conscious about the architecture of the powertrain. And that's why these two safety goals are really important for us within this context of the project. And as well, because it has the influence on the torque vectoring and so on. So these are, let's say, the main safety goals, or the relevant one that interests us. And the third group is third group of malfunctions that could be under communication, like signal delay, not completed, and so on. So different possible malfunctions that could affect as well our powertrain. This is the result of the functional safety concept. The main result is the functional safety requirements and how it's allocated on different safety goals, and where we are going at the end to put the different safety measures. I'm going to describe it there. So at the end, from those, I mean, we did it for all, of course, but as we said, as I said, the main focus will be in this safety goal 4 and 5 for these in-wheel motors. And that will be, let's say, the concept phase where it stops here. So we have this, let's say, process that we did, and that's let's say, the main results, the safety goals, the FCTI, and the functional safety requirements. But of course, while you're applying safety measures, you as well need to support this concept phase with a safety analysis, because you can subtract by yourself or by the experts different safety measures, but at the end there are different methods to support that your safety measures are well applied. Of course, here there is a group of different safety measures. In our project, we apply FDA and this STPA. Of course, the classical reliability methods like FDA, FMEA, it supports the system, and at the end is our safety analysis that provides a good hints for the developers and so on to have a really reliable system. And at the end, what we want is to avoid failures of the system. I want to develop and construct a system that really it's at the end what we describe in this failure rates really low to cover the needs of these higher ASIL components. But in the other perspective, there's this approach of the STPA that is focused on the system theory, that it goes on the direction of the assumption that systems could really escalate on the development. So here, maybe we are talking about just the powertrain would be, for example, STPA use it a lot in avionics, and for example, for automated driving vehicles, where the electronics are escalating and a lot of systems are interacting between each other and are really like, at the end, huge architectures. This STPA method provides a really fast picture of the architecture, and at the same time, a really easy way to control that, not in the way that, okay, we assume that there are methods to control the failures and reduce the number of failures, but here we assume that we cannot control that no system will never have a failure. Therefore, we have to find a method that assumes that and do the safety analysis in another perspective. And that's here what is doing STPA. So having this generic control structure that comes from the stamp accident model is analyzing the different control actions as a kind of being not interesting on what it happens in the system itself, more on those control actions. Of course, I'm not going to go into detail on the method, but really it has these 4 steps where you start from the analysis and the creation of this control structure, and it is a model, a generic model that you adapt, that you will see in the next 2 slides, and you're focused on analyzing these unsafe control actions, and from that you derive from the control actions to safe control actions, and you translate it at the end to safety measures. And this is escalating, so these 3 steps are, let's say, compared to the full analysis, relatively fast, but then you can focus, you can go to this scenario on the last step and focus exactly on each of this part of this control loop and analyze which is the relevant part that you want to do and want to analyze. And this is really the last step that is really time consuming and really here you can have the safety analysis well performed in this last part. This loss scenario, you will see here what at the end is, it looks kind, this last step. So you have the safe control actions, and of course what you want to know is the, at the end, the impact that has it in safe control actions to the overall control loop. And then you have from the actuators, for example, here, inadequate operation. So different, let's say, unsafe scenarios that you have to deal and take into account. And you will see how we translate that and adapt to our architecture. But at the end, it creates this structure of a controller, actuator, and a control process, and the feedback. That's actually what is here described in our architecture. And finally, this is the last slide, is how we use this last part that is really time consuming for our purpose. And that's what we focus on the STPA for this specific situation of the safety goal 4 and 5, where they have this in-wheel motors, where they are not connected physically, and that could have a huge impact on the safety. And here we want really to analyze this process model and what could happen if there's an inadequate control algorithm. And this process model, we try to figure out which are the different characteristics that we could have for the different inputs that the powertrain is managing, and at the end to control which are the allowed ones, the not allowed ones, and so on. And that creates a mapping that is really helpful as well, for example, for validation. And when you check there is a failure in one process that is not matching with what we studied at the beginning, then you have to somehow go through and iterate to deal with these problems on the safety.